To reach oil miles underground, you have to spin a steel pipe constantly to cut through rock. But as the hole gets deeper, that spinning pipe also has to be able to slide downward. This creates a physical contradiction. If a machine clamps onto a round pipe tightly enough to twist it, the pipe is locked in place and can't drop. But if you loosen that grip so the pipe can slide, you lose your leverage. The moment you apply massive twisting force, the metal collar slips and grinds against the pipe, generating heat and scarring the steel. Trying to squeeze a round pipe hard enough to turn it while still letting it sink is a mechanical trap. You simply cannot squeeze and slide at the same time. To find a way out, we can look at a tool you've likely used at home, a Heps key or Allen wrench. Because the key and the socket have matching flat sides, they lock together to provide perfect rotation. But since nothing is actually clamping the key, it slides effortlessly in and out of the hole even while it's turning. Drillers realized they could take this exact same concept and scale it up to a piece of solid steel that weighs thousands of pounds. This simple solution, using matching shapes rather than relying on a tight grip, is the secret that powered a century of global oil drilling. On a rig, this massive tool is called the Kelly. It's a heavy steel bar defined by its long, flat sides, usually forged into a square or a six-sided hexagonal profile. The Kelly passes through a device in the rig floor called a bushing, which acts as the socket. You can see here how the flat, white faces of the Kelly fit perfectly into the red drive mechanism. This shape separates the forces. Twisting power pushes purely sideways against the flat faces, while string weight travels straight down. The middle is flat, but the top and bottom transition into standard round threads, allowing it to screw directly into the pipe. By giving the steel flat faces, a single component handles two conflicting motions flawlessly, without the need for gears or complex moving parts. Because the Kelly is a single solid object, it has one major limitation: its length. Most are built to be roughly 40 feet long. This means the rig can only drill downward until the Kelly has slid its full length through the floor. Once the top of the Kelly reaches the table, you've added about 30 feet of new hole. At that point, the crew stops. They lift the Kelly, unscrew it, add a new joint of pipe, and start drilling again. On a typical 15,000-foot well, this stop and start cycle happens 500 times. The Kelly is more than just a piece of metal. Its 40-foot length sets the rhythm of the crew and the physical heartbeat of the rig. After absorbing millions of pounds of twisting force, the flat faces start to show their age. If the corners round off, the Kelly slips inside its socket, creating a violent hammering that destroys the tool. Cracks also form precisely where the flat drive meets the round threaded ends, the point where the steel is under maximum stress. The Kelly didn't disappear because it stopped working. It was eventually replaced because stopping every 30 feet to add pipe was simply too slow for modern drilling. Newer technologies can now drill for much longer without a break, but the Kelly remains a masterclass in using simple geometry to solve a massive industrial challenge.